Welcome all to this session on simplifying motor testing and characterization. My name is René Bastiaansen and I will be guiding you through this topic today. Let us start with a quick overview of this subject. So when we talk about simplifying motor testing and characterization, this implies there are complexities within this testing task. These complexities can be either related to the environment the motor is used in, as we can only most accurately test and characterize a motor when it is subjected to the conditions it will be used in, or the type of analysis we want to run. For a better understanding, we will first define those. When we talk about a complex system, we talk about how to handle the testing of drives with higher voltages, like for example over 1 kilovolt, more than 3 phases, or multiple motors and generators in one setup, which is a common sight in the marine industry. When we talk about complex analysis, we talk about tasks like NVH, noise vibration harshness, EQ0, space vector for complex calibration tasks, torque ripple, back EMF, dynamic power measurements, and correlating vibration and electric drive test data. Last but not least, we will look into how we can deal with these complexities. Say we want to measure electrical power and derive efficiency, taking this basic hybrid as an example. Seems straightforward, battery output, inverter output, and motor output to be measured. So we have one DC battery input, we have 3-phase AC inverter output or motor input, and we have the mechanical output from the motor, which is torque and speed. This would total in 4 power channels, 4 currents, 4 voltages, and 1 mechanical power channel for torque and speed. Right? Well, partially. This is where we can find the first levels of complexity already. Voltages to the drive to be measured can be high, over 1 kilovolt. These levels are typical in the marine industry, and we will go into detail on this in later slides. Another complexity can be the motor drive phase count. The drive might have more than 3 phases, for example. Let's take 6 or 9 phases, but we see other and bigger numbers as well. This would total in 7 for the 6-phase drive power channels needed, or 10 power channels needed for the 9-phase drive. Still 1 mechanical power channel will be needed. The higher phase count and higher voltages are not mutually exclusive. For a big part even, they have the same goal, but with its own specific advantages. Let's have a look on the reason for using higher voltages and higher phase counts in more detail. So the requirement on electrical powered systems is growing continuously. In order to generate more power out of an electrical machine, you can either increase the number of phases, increase the currents, or increase the voltage. Using more than 3 phases is doable, but it requires a more complex supply and control system. Higher currents are expensive as more copper is needed to carry the higher current. A side effect of the thicker leads is an increasing skin effect, so ideally this is avoided. Higher voltages are doable as well, and is potentially the most efficient way to achieve a higher power density. Let us divide this challenge into approaches. Either there is a requirement for more power per phase. Most efficient approach would be increasing the voltage as per previous slide, or to have the same power but less current, which can be achieved by using a higher voltages or increasing the number of phases. Benefits of the current reduction would be the requirement for less copper to carry the current, resulting in thinner cables and a weight reduction. Both approaches result in what we would call a higher power density, which contributes to a better efficiency, with the additional benefit of higher phase count lowering torque ripple as well. So far we have looked at the basic hybrid. The underlying supply system itself can also be of a higher complexity level and have interactions with how our motor behaves and the efficiency of our full drive line. Take this example with 2 generators, which could be used to scale more efficiently to higher or lower power requirements. Assuming the rest of the components are as our earlier basic hybrid setup with a 6-phase electro-propulsion drive, adding the second generator and wanting to analyze the full system would result in 9 power channels needed, 9 currents, 9 voltages, 3 mechanical power channels, 3 torque and 3 speed, and this is not where the complexity ends. What if we need to characterize the full system? We need to measure the generator internal combustion engine and the propulsion internal combustion engine and gearbox output as well. With the introduction of more electrical power, also subsystems, for example, are electrified. What we see in this example are multiple electrical uses, can be propulsion, take for example pot thrusters, pumps, or auxiliaries using the same DC source. This is starting to form an onboard grid, DC grid, or microgrid, depending on the terminology you want to use. Assuming the added drives here are smaller, 3-phase units, we would be looking at 18 power channels, 6 mechanical power channels. This will start to present a challenge with more traditional power analyzer equipment. How do we set up such a test? This shows the extent of the system level complexity, but also introduces us to some of the analysis level complexities when designing and or implementing these systems. Now, why do we care about the complexity? Why not characterize component by component and that's it? As all components are on the same grid, they can influence each other. Will clutching in and out one of the loads or generators not cause the other generator to oscillate out of control, for example? And how can we optimize component interactions and efficiencies without actually measuring and testing in the environment they will be installed in? So, now being introduced to the possible system level complexities, let's have a look into analysis related complexity, noting analysis and system level complexities are not mutually exclusive. So when we talk about complex analysis, analysis again can be on a component, subsystem or system level as just introduced. This depending on the type of analysis. A common type of analysis is an efficiency map, or in case on component level for the motor, a motor map. This looks something like this. The efficiency map is created driving either a component, motor for example, or a subsystem, or a full system, motor, inverter and supply system through a range of set points of, for example, torque and speed. This process is quite straightforward, but it can be time consuming, and here is why. So let's say our map contains 200 points in terms of speed and load, and mind, this is not a very big map. We test at 10 different temperatures, as temperature influences performance. 5 different generator stages, as we want to do the full drive line, so we have the different loading conditions of the 2 generators. 5 states of charge of the battery, as this again influences performance, and this totals up in the multiplication of those. So 200 by 10 by 5 by 5 is 50,000 measurement points. Now, if each measurement takes up to 10 seconds, might be the time we need for our power analyzer reading to stabilize, for example, we end up at 139 hours of testing. Bringing down this test time would be beneficial, we can see in the table to the right, and how we can do this we will discuss later. In this case, we also need to note we are not even considering time needed for the transition of the machine from one set point to the next. We are not accounting for heating up and cooling down of the machine, as we need to keep the temperature stable during testing, and loading the machine will cause it to heat up. And we are also not considering other parallel analysis requirements and rerunning of tests in case of error at this point. Some of the complex analysis we like to do on a subsystem level, like machine calibration, ensuring our inverter and motor at given set points operate as efficiently as possible. This is called calibration. The DQ0 transformation is used by engineers to control the electric powertrain and is programmed into the motor controller. This needs to be verified, and the same applies to space vector analysis. These control equations should be recorded, made synchronous to the measurements like torque, so you can analyze control response. When implementing motor control strategies, there is a need to get the motor parameters. These are usually stator resistance and inductances, and the magnet flux linkage or the back EMF constant. The stator resistance and inductance can be obtained rather easily with line-to-line impedance measurements for different rotor positions or through a short circuit test. The back EMF is usually obtained by means of a no-load test. This method is simple at first sight, but it has disadvantages. If the motor is wound to get non-sinusoidal back EMF voltages, then the calculated magnet flux is not correct since it must correspond only to the fundamental components. If the speed is not constant, either by a non-ideal speed regulation or eccentricity of the rotor shaft, the voltages will also fluctuate and influence the calculation. Another interesting one, already briefly introduced, is vehicle energy measurement. What happens to components when other loads change? Machines clutch in and out, for example. For example, a drive or a generator starting up or shutting down. It's about control architecture with analysis requirements close to calibration, discussed before, but just not focusing on efficiency, but on the control. Here, stability is the primary concern. We do not want all our systems to stop and lose vessel control when we engage or shut down a generator or auxiliary system. Here we find terms like vehicle energy management or even DC or microgrid analysis, as that is what we are slowly but surely building, a small energy grid. So we want to measure what happens to components when order loads change in order to optimize the control architecture and optimize stability. Having a continuous stream of raw data and not just calculated results is key here. We see an example plot of such a measurement at the bottom of the slide. And not to forget about NVH, noise vibration harshness, where also raw data plays a key role. We care about NVH for various reasons. For human comfort, for operators not being subjected to harmful vibrations and noise during the routines. For fatigue, certain levels and frequencies of vibrations can damage systems and components. Or if we look at luxury applications, it's really just all about the comfort. We look at NVH either on a system or on a component level. It is interesting to do on a system level, where different vibrations can overlap, amplify and cause trouble. With our electrical drives exciting components causing vibrations, we can find correlations between frequencies found in the drive current measurements and the actual vibrations measured at the machine or the structure. Correlating these can help identify and fix such issues, for example, by changing the machine control strategy or the inverter software, which demonstrates the use of combined electrical, power and NVH measurements. This also applies to topics like torque ripple introduced by the electrical machine. This torque ripple introduced into our gearboxes can cause effects like gear chatter, wearing out and destroying gearboxes prematurely. This can be correlated against the machine excitation current, and a change of the controls or even a machine design here could be needed. Here, correlation between NVH and electrical power measurements joining the electrical and mechanical world helps us to pinpoint the area of interest. So let's go back to our measurement system design targets and add in the analysis complexity as well. So for the system complexity, we require an expandable amount of input channels for both electrical and mechanical power, higher voltage input ranges, which should be safe for the equipment, for the user, as well as compliant to safety standards, and should be capable of dynamic measurements to acquire any load steps of machines clutching in and out. In terms of the analysis complexity requirements, the system should be capable of capturing other measurements, other quantities like temperatures, vibrations, flow, sound, controls synchronously. Raw data should be recorded for detailed analysis, and advanced analysis capability should be available for calibration tasks, control behavior, mappings, and NVH. So, which solution will we propose here? What we propose at HBK is our eDrive power analyzer solution. This is a modular system that allows adding more power channels where needed, but also provides capabilities to acquire any other electro or mechanical quantities, like temperature, flow, torque, and speed, pressure, force, you name it, all into one system and capable of interfacing with analysis software as well as automation systems. So how do we deal with the challenge of the higher voltage levels? Well, we have different levels of voltage inputs available, either directly into the power analyzer boards for 1 kilovolt RMS or 1500 volts DC, with a differential probe up to 5 kilovolts, and for higher voltages we can use high voltage dividers combined with fiber optic isolated front ends. Either with a fiber directly into the power analyzer using a fiber input board, or with a separate conditioner as a retrofit solution. And do note all the methods ensure maximum safety within its specific voltage input range. Having all these inputs available, how do we deal with setting up the measurement for a complex system? This is powered by our software. The eDrive Creator allows for easy configuration, and let's start with a 6-phase motor for we see the setup here included with the inverter and the DC supply. You need a 9-phase setup, just add 3 more phases to the inverter component output and connect it to the motor. Same for complex systems. Here we map a quad thruster setup to the same interface, allowing for custom power and efficiency measurements, allowing for efficiency and control testing, both on a system and component level. Furthermore, we can minimize test time through raw data collection and real-time calculations. These real-time calculations are enabled through a clever algorithm called cycle detection, and more details on that one in the next slides. After mapping our solution, complex or not, we can set up our analysis. This can be done on an individual component or on a system level and start, for example, efficiency mapping. Also, more advanced mappings like iron, copper, and friction losses or MTPA, maximum torque per ampere, can be created. More importantly, test time can be significantly reduced as there is no settling time like in many traditional solutions. As soon as the dyno itself is stable and half a cycle of the current is detected, you have the result, and basically you can test as fast as the dyno can change a set point to a stable setting. Control and calibration algorithms for analysis like DG0 and space vector are available. See some examples below. And in terms of parameter extraction, we offer an enhanced method for back EMF testing, which allows for non-sinusoidal and variable speed type of signals. This is not where it ends. There are far more capabilities, too many to name, but let's take a look on how this all is possible. When calculating power, instantaneous signals need to be acquired and have power calculations performed on them. Most power analyzers do not store these raw signals, and most data recorders are not accurate enough to provide power measurements. The eDrive system is unique because it stores the data at a high rate for extended periods of time and provides the high accuracy power measurement needed for efficiency measurements. These signals can also be visualized in real time, similar to a scope. Having the recorded signals gives transparency to your measurements. You don't just get the power value, you get all the data that went into it, which also allows you for correlation. To calculate AC electric power, at least half a cycle of the fundamental is needed. Determining the time frame for half a cycle can be difficult because the frequency in rotating machinery often is changing. The eDrive system has a digital signal processor where we filter the phase A current in real time to determine the half cycle time basis. Then, what makes our system unique is that we calculate the power on each half cycle period in real time. By doing a calculation each half cycle, we can get accurate measurements even if frequency is changing. And by doing the calculations in real time, we can cut down on post-processing and offer signals as feedback to control systems or deliver faster results, for example, into the motor or efficiency maps. Providing a recording of the cycle time basis also gives an added layer of transparency to the test by letting users know how their calculation was done. This cycle detect allows measurement of signals as frequency is changing, even if there is a step change like we discussed before with our machines glitching in and out. It is what enables dynamic testing and characterizing real-world scenarios. Now onto our last complex analysis challenge, NVH. By recording all our raw data into one system, being both our electrical power measurements as well as our sound and vibration signals, we can start doing first-level analysis online. Even more in-depth NVH frequency domain analysis and correlation in post-process is possible using dedicated applications like BK Connect, all from one hand and all from one supplier. Here we see an example of torque ripple during a machine run-up, where a resonance is excited by a few higher orders. We can nicely correlate between the time and frequency domain, helping us to pinpoint the cause. And then last but not least, feedback and communication with the control system makes test automation possible. Standardized buses and real-time equations combined with a variety of control options simplify the automation process. Here the eDrive system offers a variety of communication methods and control options for seamless integration with all data stored locally or onto a PC hard disk. To summarize, eDrive allows for simple data collection of electromechanical signals, fast and accurate efficiency measurements, future-proof testing capabilities through a modular concept, and offers auditable testing and advanced analysis through stored data and public equations. It also allows you to provide feedback to control systems. And that brings us to the end of this session. Thank you, and feel free to reach out to us with any questions. You can follow the URL for more information or scan the QR code with your phone to end up at the same website. Thanks for your attention and hope to see you later.